A single black hole can delete 100% of the universe's fundamental information forever. In 1974, Stephen Hawking published a Cambridge paper proving that these massive objects eventually evaporate. But if Hawking was right, the atoms in your body possess no permanent history or future. Leonard Susskind sat in the back of the lecture hall. This disagreement ignited a 30-year war to determine if information scrambling has a physical limit. That introduced the world to Hawking radiation and, with it, a terrifying paradox that threatened. Hawking argued that black holes eventually evaporate, shrinking away over eons until they vanish entirely into a puff of thermal radiation. The problem was what happened to the information inside. According to Hawking's initial calculations, the information contained in everything that ever fell into the black hole, the specific arrangement of atoms in a star, the data in a lost satellite, the very data of an unlucky astronaut, was simply deleted from the This was in the world of quantum mechanics, unitary evolution is the sacred law stating that the past information, like energy, must be conserved. If you burn a book, the information in its pages isn't gone, it is just scrambled into the smoke, ash, and heat. If you were a godlike entity with enough patience, you could theoretically piece the book back together. But Hawking was claiming that black holes were the universe's only true delete button. He suggested that once something crossed the event horizon, its history was severed from our universe forever. Susskind, working at Stanford University, realized the stakes immediately. If Hawking was right, the entire foundation of modern science would collapse because the predictability of the universe would vanish with the information. This sparked the legendary Black Hole War, a period of intense intellectual combat involving giants like Gerard Hooft and later John Preskill from Caltech. They had to find a way to save information without violating the no-cloning theorem of quantum mechanics. They began to suspect that the event horizon wasn't just a point of no return, but a sophisticated frontier where information was being processed at a rate that defied imagination. This conflict forced the community. If information isn't destroyed, how quickly is it hidden? And is there a physical limit to how fast? Now I want you to imagine a secret. Not a small secret, but a fundamental piece of information. If you wanted to hide that secret from For decades, the answer seemed obvious. You throw it into a black hole. Once it crosses that event horizon, it's gone. But by the early 2000s, the Black Hole War between Stephen Hawking and Leonard Susskind had reached a fever pitch, and the stakes were nothing less than the survival of quantum mechanics. If information truly vanished, the law of unitary evolution, the rule that says the past can always be reconstructed, Susskind had argued that information must be preserved on the surface of the black hole, the event horizon, like a 2D hologram. But a new question emerged, one that was perhaps even more haunting. If the information is saved, in 2007, a young physicist named Patrick Hayden, then at McGill University, teamed up with John Preskill from Caltech to investigate this using the language of quantum information theory. They published a paper with a provocative title, Black Holes as Mirrors. Now, when you think of a mirror, you think of light bouncing off a surface instantly. But black holes are supposed to be the ultimate traps. Hayden and Preskill discovered something that shocked the community. They realized that if a black hole has been around long enough to emit about half of its mass through Hawking radiation, it becomes maximally entangled with the radiation it has already sent out into the universe. In this state, the black hole acts like a quantum mirror. If you throw a new piece of information into an old black hole, that information doesn't just sit there for eons. It is processed, scrambled, and reflected back out into the Hawking radiation almost immediately. But what does immediate? This is where the concept of scrambling becomes vital. Think of a drop of food coloring falling into a glass of water. At first, it's a localized dot, highly visible, easy to track. That's your information. But as you stir the water, the ink spreads. It tangles with the water molecules. Eventually, the water looks a uniform shade of blue. The information isn't lost. Every molecule of ink is still there, but it is scrambled. To recover the original shape of that drop, you would need to Hayden and Preskill showed that black holes are the most efficient stirrers in nature. They don't just mix information, they obliterate its local. A year later, Leonard Susskind and Yasuhiro Sekino took this a step further with their paper, Fast Scramblers. They wanted to find They conjectured that no system in the universe could scramble information faster than a time proportional to the logarithm of the number of its degrees of freedom. Mathematically, this is written as the time being proportional to the natural log of n. To understand why this is so fast, you have to appreciate the power of logarithms. If you have a system with 10 to the power of 80 degrees of freedom, roughly the number of atoms in the observable universe, the logarithm of that number is just 80. In the world of black holes, this means that even if a black hole is the size of a galaxy, it can smear a single bit of information across its entire event horizon in a fraction of a second. This scrambling time is the forbidden speed limit of reality. It's the point where the universe says no faster. By proving that black holes saturate this limit, Hayden and Susskind revealed that these gravitational monsters are not just graveyard for stars. They are the ultimate high-speed quantum computers processing the fabric of reality at the very edge of what physics permits. By the year 2015, the theoretical physics community had reached a fever pitch. We knew that black holes were the fastest scramblers in the cosmos, but the underlying reason, the absolute mathematical proof of a universal that was until Joan Maldacena, Stephen Schenker, and Douglas Stanford published their definitive work titled A Bound on Chaos. This wasn't just another paper, it was a decree from the universe itself. Imagine you're at a high-stakes poker table where the house always wins, not because they're cheating, but because there is a fundamental limit to how fast you can even shuffle the cards. Maldacena, Schenker, and Stanford proved that the rate at which quantum chaos grows has a hard ceiling. In classical physics, we talk about the Lyapunov exponent, which is just a fancy way of describing how quickly two nearly identical paths in a system will diverge. It's the butterfly effect, a tiny flap of a wing in Brazil causing a tornado in Texas. But in the quantum realm, things are much blurrier. You don't have neat little trajectories, you have operators and wave functions. The researchers looked at how a local operator, something small and manageable, grows over time to affect everything else in the system. They discovered that this growth, this spreading of chaos, is bounded by a very specific value, 2 pi times the Boltzmann constant times the temperature, all divided by the reduced Planck constant. Mathematically, it looks like a simple fraction, but philosophically, it is a wall. This limit, which we often call the Planckian time scale, dictates that the hotter a system is, the faster it can scramble, but it can never, ever go faster than that ratio. This was the first time we realized that thermodynamics and quantum mechanics were locked in a tight embrace to prevent information from moving too quickly. If a system could scramble faster than this bound, it would essentially break the logic of the universe. What makes this so profound is that almost every system we know, a block of ice, a swirling nebula, a cup of tea, is nowhere near this limit. They are sluggish, disorganized, and slow. But black holes are the Olympic sprinters of the quantum world. They saturate the bound. They hit that mathematical wall at full speed and stay there. This discovery reinforced the idea that black holes aren't just giant vacuum cleaners. They are the most efficient, most chaotic, and most tightly regulated information processors allowed by the laws of physics. When we say a black hole is a fast scrambler, we aren't just using a figure of speech. We are saying it lives exactly at the forbidden edge of reality's speed limit, performing the maximum amount of work on information that the fabric of space-time can possibly sustain. This bound on chaos effectively bridged the gap between the heat of a system and the flow of information, proving that at the highest temperatures and the smallest scales, the universe has a built-in governor that prevents reality from dissolving into total instantaneous noise. Imagine a room filled with people where everyone is trying to tell us, in most physical systems, that information travels like a rumor through a small town. It moves from one person to the next, slowly diffusing through the crowd. But in 2015, Alexei Kitaev, a brilliant and soft-spoken physicist at Caltech, introduced the world to a mathematical construction that behaved more like a flash mob of pure chaos. This is the Sachdevya-Kitaev model, or the SICK model for short. It wasn't a new discovery in the traditional sense. Subir Sachdev and Jinwoo Ye had proposed a version of it back in 1993 to describe the strange behavior of magnets. But Kitaev saw something in it that no one else had noticed. He realized that this cluster of particles interacting randomly with every other particle in the system simultaneously was the first non-black hole system ever discovered that saturated the forbidden speed limit of reality. This was a massive moment for the community. You have to understand, up until this point, black holes were the lonely champions of the universe. They were the only things we knew that could scramble information at the maximum rate allowed by the laws of physics. But here on Kitaev's chalkboard was a simple quantum system, a collection of particles with no gravity involved whatsoever. That was doing the exact same thing. It was scrambling information at a rate proportional to its temperature, hitting that 2 pi t bound exactly. It was as if Kitaev had built a black hole out of nothing but math and quantum logic. This suggested something profound about the nature of the universe. If a simple quantum system can mimic the most complex gravitational object in existence, then maybe gravity itself isn't a fundamental force. Maybe gravity is what we call an emergent property. Think about the temperature in your room. If you look at a single molecule of air, the concept of temperature doesn't exist. Temperature only emerges when you have a billion molecules bumping into each other. The SICK model showed us that the gravity of a black hole might just be the collective behavior of deeply entangled quantum information. By studying the SICK model, physicists like Juan Maldacena and Douglas Stanford began to see that the way these particles scramble information is mathematically identical to the way space and time warp near the horizon of a black hole. It became a lab for quantum gravity. We could finally peer into the engine room of the cosmos without needing a telescope. This little model proved that the laws of information and the laws of gravity are actually two sides of the same coin. It tells us that the very fabric of time might be woven out of the way information spreads through the quantum world, a process so fast, so chaotic, and so fundamental that it defines the very limits of what is possible in our reality.